Welcome to CBSEasy.
You know, numbers can seem kind of chaotic, right? But the truth is, they all follow this set of really beautiful, elegant rules. Today, we're going to master some of those rules. We're going to tackle 6 classic challenges and turn what looks like a math test into a series of, well, really fun puzzles. Okay, let's dive in. So here's our game plan. We're going to start with some foundational stuff, then we'll uncover the secrets hiding in decimal points, prove why some numbers are built the way they are, and we'll wrap it all up by solving a really clever remainder puzzle. It's going to be a full workout for your logical brain. All right, first up, we're getting back to basics with 2 of the most fundamental ideas in number theory: the highest common factor, the HCF, and the lowest common multiple, the LCM. But we're also going to check a crucial rule that ties them all together. And here is our first challenge. So we need to find the HCF and LCM of 84 and 126. Then, for part 2, we have to verify that neat little formula at the end. This is a great test of our ability to break numbers down to their absolute core. This table here makes the whole process super clear. Once we break 84 and 126 into their prime factors, finding the HCF is easy. We just take the smallest power of each prime factor they have in common. So that's a 2 to 1, a 3 to 1, and a 7 to 1, which multiply together to get 42. Then for the LCM, we do the opposite. We take the greatest power of every prime factor that shows up in either number. That gives us 2 squared, 3 squared, and 7 to 1, for a total of 252. See? The table does all the heavy lifting. And here is the payoff. We multiply our HCF and LCM, that's 42 times 252, and we get 10,584. Then we multiply our original numbers, 84 times 126, and guess what? Same exact result. The rule holds true. It's just a fantastic way to double check that you got it right. Okay, moving on. Let's see how those same prime factors can reveal the hidden nature of fractions. We're about to find out why some fractions create decimals that just stop, while others seem to go on forever and ever. So here's the secret, and it's actually really simple. If you want to know if a fraction's decimal will end or terminate, you only have to look at the prime factors of the denominator. If the only prime factors you find are 2s and 5s, the decimal will terminate. That's it. And the really cool part, the number of decimal places is just the highest power you see on either the 2 or the 5. So with that rule in our back pocket, let's put it to the test. We've got the fraction 29 over 4,000. Without even thinking about using a calculator, can we predict exactly how many decimal places it's going to have? Nope, no long division needed here. We just focus on that denominator, 4,000. We break it down and see it's only made of 2s and 5s. Specifically, it's 2 to the power of 5 times 5 to the power of 3. So what's the highest power there? It's 5. And just like that, we have our answer. The decimal for this fraction will terminate after exactly 5 places. All right, let's shift gears a little bit. We're moving from how to calculate to how to prove. This next bit is all about understanding the fundamental nature of a number just by using logic. Okay, check out this puzzle. We have this expression, 7 times 11 times 13 plus 13. Now, the question isn't, what's the final number? It's, why is it a composite number? And remember, a composite number is just any number that has more factors than just one in itself. So, as this slide says, you could multiply it all out, but that's taking the scenic route. The direct path here is all about logic. Instead of reaching for a calculator, let's just look at the structure of the expression. There's a pattern, a clever shortcut that will reveal this number's identity without any heavy lifting. And here's the really elegant solution. Do you see how 13 appears twice? Well, we can factor it out. This completely changes the expression into 13 multiplied by, 7 times 11 plus 1. That simplifies down to 13 times 78. And boom! Instantly, we can see this number is divisible by 13 and by 78, not just one in itself. And that, by definition, makes it a composite number. Proof complete. Now for what might be one of the most famous and honestly beautiful proofs in all of mathematics. We're going to prove, with pure logic, that some numbers just can't be written down as a clean, simple fraction. Let's dive into the world of irrational numbers. You and I both know that the square root of 3 is irrational, right? We just accept it. But how would you actually prove it to someone with absolute, undeniable, logical certainty? Well, that's our mission for this section. To pull this off, we're going to use this brilliant technique called proof by contradiction. It's kind of like being a detective. We're going to assume the opposite of what we want to prove. We'll pretend the square root of 3 is a totally normal rational number, and then we're just going to follow the clues until the whole case falls apart. Okay, let's walk through this together, step by step. First, we assume root 3 is rational. This means we can write it as a fraction, a over b, in its simplest possible form. And that means a and b share no common factors. They're coprime. Now, if we square both sides and move things around, we get 3b squared equals a squared. This tells us a squared has to be a multiple of 3. Now, there's a key rule that says if a number squared is divisible by a prime, like 3, the original number also has to be divisible by 3. So a is a multiple of 3. Let's call it 3c. Now we substitute that back into our equation, and we get 3b squared equals 3c squared, which simplifies to b squared equals 3c squared. See where this is going? This means b squared is also a multiple of 3, which means b itself must be a multiple of 3. And that's our problem. And this is it, the moment the whole case breaks. We started with one rock-solid condition, that our fraction a over b was in its simplest form, that a and b had no common factors. But our own logic just proved that they both have to be divisible by 3. That's a flat-out contradiction. Our logic has collapsed on itself, and the only possible reason for that is that our very first assumption, the thing that started this whole chain, was wrong. So the square root of 3 cannot be rational. It has to be irrational. Okay, for our next trick, let's explore how we can prove that entire classes of numbers all have to follow a very specific algebraic pattern. We're about to uncover a hidden structure in all odd numbers. So here's the claim. Pick any odd positive integer you can think of. Anyone. Square it. The result can always be written in the form 8 times some number plus 1. Think about it. 3 squared is 9, which is 8 times 1 plus 1. Works. How about 5? 5 squared is 25, which is 8 times 3 plus 1. Yep, that works too. But how do we prove this is true for every single odd number? Well, we use algebra. We can write any odd integer as 2n plus 1. If we square that, we get 4n squared plus 4n plus 1. Now let's just factor that a little bit to get 4n times n plus 1 plus 1. And here's the magic bit, the key insight. Look at n times n plus 1. These are 2 consecutive integers, right? Like 3 and 4 or 8 and 9. No matter what, one of them has to be even. And an even number times anything is always even. So we know for sure that n times n plus 1 is an even number, which we can just call 2m. So we substitute that back in and we get 4 times 2m plus 1, which of course simplifies to 8m plus 1. The structure was hiding there the whole time. Okay, for our final problem, we're going to put everything together to solve a classic word puzzle. This one seems really tricky at first, but it just needs one clever insight before we can use a tool we already know how to use. Okay, let's read this one carefully. We need to find the largest number that divides into 3 different numbers, but leaves 3 different specific remainders. Whoa. Okay, that sounds way more complicated than a simple HCF problem, doesn't it? And here is the aha moment. The remainders are what's making this whole thing a headache. So, what if we just took them out of the equation? Think about it. If our mystery number divides 180 and leaves a remainder of 12, that must mean it perfectly divides 180 minus 12. So, we just subtract the specific remainder from each number. That gives us a new set of numbers, 168, 234, and 300. And our mystery number has to divide all of these perfectly. So the complicated question has just transformed into what's the highest common factor of 168, 234, and 300? And hey, that's a problem we already know how to solve. The HCF is 6. So let's just step back and look at the awesome toolkit we've put together today. We used prime factorization to nail HCF, LCM, and even predict how decimals behave. We shifted gears into logic, using simple factoring to prove a number's identity. And then we used the really elegant power of proof by contradiction. And finally, we learned the subtract the remainder trick to reframe a tough puzzle into an easy one. Each of these is a powerful tool for your mathematical thinking. And here's something to think about as we wrap up. These aren't just abstract puzzles for a classroom. The deep, fundamental properties of prime numbers and integers are the absolute bedrock of modern cryptography, the stuff that protects your bank account, your private messages, everything. It really makes you wonder, what other profound secrets are still hiding in the simple numbers we use every single day?
Thank you for watching with us. See you next time.